Hello, it's Dumplet here. Here's an item on algebra. Evaluate the series 2 over 1 plus 2 squared times 2 squared minus 2 plus 3 over 1 plus 3 squared times 3 squared minus 2 plus 4 over 1 plus 4 squared times 4 squared minus 2, and so on and so forth. Credits to the Art of Problem Solving community for this item. As usual, pause this video if you'd like to give this item a try. But if you're done, let us dive into the solution. Alright, so as you can see here, we have like an infinite series, and we can try to make some observations here. Every term of the sequence, everything that we're adding, it follows a general format. Look, if I replace the 2, the 3, and the 4 by a general variable, let's say n, then each of these terms are of the form n over 1 plus n squared times n squared minus 2. And technically speaking, we're getting the summation of this from n equals 2, the first value, as you can see here. Well, it doesn't have an n, so until infinity. So technically like that. So mathematically speaking, this sum is just the same as this one. So let's try to see what this, this rational expression here tells us something. Now, let's try to expand the denominator. So 1 plus n squared times n squared minus 2. Simply expand this part. And if you do that, that's going to be equal to n to the 4th minus 2n squared plus 1. And this is actually nice because it is factorable. In fact, this is n squared minus 1 quantity squared. And the n squared minus 1 inside, it's still factorable into n minus 1 times n plus 1. So the denominator is actually equal to this thing entire squared. So factored form, it's going to look like that. And let me just distribute the exponents here so that it becomes like this. So every term is of this format now, n over n minus 1 squared times n plus 1 squared. And then, ideally speaking, there is we want to like decompose into partial fractions, because it is kind of expected that whenever I have these kind of sums, we want stuff to cancel, or maybe it's going to telescope to a nice value, because that's how at least we can simplify the sum, because there isn't really a direct formula to tell us what's the sum of at least this thing over here. So I try to make some observations since I want to like decompose into partial fractions. Well, it might be nice to decompose into two fractions with denominators, as you can see here, n minus 1 quantity squared and n plus 1 quantity squared. And this is the thing I got, but this thing is not totally random. It's not really something that comes to our mind like immediately. So let's try to see how we got this yellow underlined term. Now, there is a standard technique to solve partial fractions, to decompose into partial fractions. Probably you can look that up. But in my case, well, it's kind of easy to get the partial fractions, because if I expand n minus 1 squared, I'll have n squared minus 2n plus 1. And if I expand n plus 1 squared, that's going to become n squared plus 2n plus 1. And they differ by 4n. So it's kind of nice because I have an n in the numerator. So all I need is just to have a factor of this 1/4 in the front. Because, for example, if you try to evaluate this, if you try to put this into one fraction, it's going to be 4n over the product of the denominator. So hence I need the factor of 1/4. So sometimes getting the partial fractions, it might be a little easy. It might be obvious at first glance. But anyways, if we can do stuff, if we can decompose the fractions, this expression into fractions, so in partial fractions, then we might be able to, then the sum might be able to telescope. So it might be easier to realize that, oh, this must be the value of the sum. And it will be, because now that we know that each term can be rewritten in this format, as you can see here, you can plug those values back, so 2, 3, 4, and so on. So if n equals 2, it's going to give this term 1/4 times 1 over 1 squared minus 1 over 3 squared. Again, I'm just substituting the n's here into the partial after I did the partial fractions. And same for the n equals 3 and n equals 4, as you can see here. And it's actually a nice summation, because after I factor the 1/4, since all of these terms have 1/4, I know that I can do 1 over 1 squared minus 1 over 3 squared, and and then plus 1 over 2 squared minus 1 over 4 squared. And you guys can kind of see some of these terms will actually cancel. And let's try to see this in detail here. For example, here, this minus 1 over 3 squared, it cancels nicely with this plus 1 over 3 squared. And it's kind of expected that this minus 1 over 4 squared, although it's not visible, but there is a term here that's, since we're going to take the sum until infinity, until n equals infinity, so there is this 1 over 4 squared minus 1 over 6 squared term. So this 1 over 4 squared is going to cancel with this 1 over 4 squared. And following this pattern, we know that everything here was going to be cancelled. So what remains in the sum is just simply the following. So the 1/4 times 1 over 1 squared plus 1 over 2 squared, because everything else is just going to cancel. So this sum is actually, the only thing that we have to evaluate right now is just this. And this is the concept of telescoping sums, because you can use the concept that it's going to telescope, or it's going to, after we do the cancellations of terms, for example, as we did here, it's going to just telescope, quote unquote, converge to this sum. So all we have to do is evaluate this. So 1/4 times, well, 1 over 1 squared, that's just 1. 1 over 2 squared, that's 1/4. So 1/4 of 1 plus 1/4, that's 5/4. Evaluating this, we're going to get that the initial series is just equal to 5 over 16. And this will be our final answer. Hopefully you guys learned something new from this video, and I'll see you in the next one. Bye bye.